So let's take a look at an astable multivibrator and see how it works. If we look at the circuit, we will initially identify that what we have is what looks like a Schmitt trigger, meaning an op-amp with some positive feedback, except the input signal, or what will normally be the input signaling an inverting Schmitt trigger, has now been replaced with an RC network. Now, because this is in essence a Schmitt trigger, there are two possible states for the output. It's going to be sitting at, let's imagine that this is an op-amp with a certain saturation voltage. It's going to be sitting at the positive saturation voltage or the negative saturation voltage at the high or low states, more generally speaking. And then notice that there is no input signal, and so there needs to be something within the circuit that is going to allow that output voltage to switch from the positive state or from the high state to the low state and vice versa. And that something is going to be the charging and discharging of the capacitor through the feedback resistor R. Now, a question that may come to mind is, well, if there is no input signal, how do we know that Vout is going to be sitting at one of the two high or low states? Why not sitting at zero? And the answer is that there's always going to be some offsets within the circuit that are going to force the output to move to either one of the output voltages, either high or low. It's unpredictable which one, but after all, the purpose of the oscillator is that it will be generating a periodic waveform, so we don't really care where it starts. It's just gonna keep going periodically from high to low. So let's imagine one of the two states. Let's assume that Vout is sitting initially at positive saturation voltage. And if Vout is sitting at the positive saturation voltage, then because we have a voltage divider network going to V plus, I'm going to indicate that as V plus and the other input terminal as V minus, then we have that V plus is going to be the result of voltage division. So it's going to be equal to R2 divided by R1 plus R2 times the output voltage, which we just said is Vsat. Now what's going to happen on the other side is that capacitor C is going to start charging, and so the V minus voltage is going to start going from zero if the capacitor was initially discharged, but it's going to start increasing. So V minus is originally less than V plus. That's how we got Vout sitting at positive Vsat. But increases towards the positive saturation voltage as C charges, let's say. And, ideally, if it continued to charge, it will reach finally the saturation voltage. However, before it reaches the saturation voltage, once it reaches this voltage, which I'm going to label as V1 there, once it reaches the voltage of V plus and it surpasses it a little bit, then the output is going to flip. So we can say when V minus becomes greater than what I've labeled as V1, then it forces V out to the negative saturation voltage. Now, as V out goes to the negative saturation voltage, V plus now becomes negative R2 divided by R1 plus R2 times Vsat, because again, it's the result of voltage division. And V minus is initially greater than that because it's initially sitting at V1. This is, we can identify it as negative V1. It's just the opposite of what we labeled previously as V1. So V minus is initially greater than that, but it decreases towards negative Vsat as C discharges. And if it were allowed to discharge completely, ultimately it will reach negative Vsat, which is the value of V out. But once it reaches once it becomes less than V1, then the output will switch again to positive Vsat and we will be back at the beginning. And so we will be resuming the process cyclically. The result of this, if we wanted to plot it graphically, as far as Vout is concerned, is that Vout is going to be switching between positive and negative saturation voltage without the need for any input, without the need for any triggering signal. So this is going to periodically move between positive saturation and negative saturation. The positive input voltage, what we have labeled as V+, is also going to be a periodic square wave. So it's going to look like the output, except it's a voltage divided version of the output, and so it's going to have the exact same shape, except it's going to be moving between smaller voltage levels, namely what we've labeled as V1 and negative V1. And our negative input, what we have labeled as V minus, it's going to be, as we mentioned, trying to charge and discharge towards final values of Vsat and negative Vsat. So we will try to go towards Vsat, except once it reaches V1 or negative V1, it's going to have to turn the opposite direction. So, because that is the moment when the transition occurs. And so if I were to represent it, once it reaches this point, then it's going to go negative. Once it reaches that point, it's going to go positive. Positive. Once it reaches that point, and the V plus goes negative, and this is going to start discharging, and so forth. And so basically, this will be the charging and discharging of that capacitor that gives the name to the circuit relaxation oscillator. And again, what we will have at the output is just a periodic square wave signal. And notice that with this type of oscillators, that's what we typically get. We don't get a sinusoidal signal. We will talk about sinusoidal oscillators later on, but we get a non-sinusoidal periodic waveform.